Welcome to the virtual learning course, What's Coming Down the Pipe? A discussion on sewer capacity studies. My name is Sarah Snavely and I will be moderating today's session. Just a few housekeeping items before we get started. This is going to be available both audio and web conference, and it will last approximately 60 minutes with Q&A at the end of the presentation. So if you have questions at any point in time during today's presentation, just go ahead and submit them via the Q&A button at the bottom of your screen, and Chris and I will handle those at that point in time. So, also, please note that this presentation is worth 1 AIA HSW credit. We will be sending out certificates to all attendees at the end of the presentation. So be on the lookout for those. If you are an architect and you did not submit your AIA number upon registration, go ahead and send that to me via email and we'll make sure we get that submitted to you as well. Everybody will receive a certificate of completion today though. And now, if you've been wondering about capacity improvements to sanitary sewer collections, you've come to the right place. And it's my pleasure to introduce today's speaker, Chris Petrie with Timmons Group. Chris, take it away.
Great, thank you, Sarah. And thank you everyone for your time this morning. Today we're going to be discussing downstream sewer capacity studies. These studies are important for any project that is anticipated to increase the flow of sanitary sewer in an existing system. So extremely important. Learning objectives for today, I think it's important that everyone have a general understanding of what collection system infrastructure looks like. We want to understand the information that we as engineers need to collect to complete a capacity study. We're going to learn a little bit about some typical methods of increasing capacity in a collection system, and then develop an understanding behind the variable cost and schedule for capacity studies. So to accomplish those goals, we're going to talk about obviously collection system infrastructure, the steps necessary in a capacity study, the recommended schedule for when in a project timeline to complete capacity study, and again, cost variability. And as Sarah mentioned, Q&A at the end. I will do my best to get to everybody's questions, but if I can't, I will provide my contact information, and please don't hesitate to email or call me at your convenience. So with that, let's talk about collection system infrastructure. When discussing sanitary collection systems, there's two main types. You've got a gravity-driven system, gravity sewer, or a differential pressure system like a pump station. So looking a little bit deeper at gravity sewers, two main components. You've got your sewer pipes, and then you've got manholes, which are basically the points of connection between pipes. Some of the benefits of a gravity sewer, well, it's gravity powered, so no additional energy is needed to move the wastewater down line because it is just large open pipes. It easily handles grit, debris, any solids, sometimes critters. I've seen rats, I've seen snakes, and I've seen plenty of cockroaches. There's also easy access for inspection and cleaning. Some of the disadvantages of a gravity system, well, it's gravity powered, so it only works downhill. So if your site's got to change or an increase in grade, the sewer's got to maintain the downward slope. So there's a potential for some deep installation. Precise construction is required. Typically, these systems are designed with minimal slopes, and because slope is an important part of the capacity of the system, those slopes it's very important that those slopes are met. The system is open to atmospheric pressure, so that means water, non-sewage flows can get into the system, inflow and infiltration, so rainwater or groundwater. And if water can get out of the system, it also means that if water can get into the system, it means that water can get out of the system. So if there's a blockage or restriction in flow, there's a potential for sanitary overflows. They're also not very easily relocated. I mentioned the specific slopes that they're designed for. So if there's a relocation that adds length, then meeting that minimum slope is going to be difficult. And there's no way to increase capacity without replacement. Now, there is one caveat to that I'll touch on in a bit, but for the sake of this discussion, replacement is generally the only way to increase capacity. Now, components of pump stations. We've got a holding tank we call a wet well. Obviously, there's pumps, and typically in a pump station, you'll have at least 2 pumps. That's not always the case. Smaller stations will be what we call a simplex or a single pump, but generally speaking, wastewater pump stations will have at least 2 pumps. The pressure pipe we call force main. Screening and grinding equipment is responsible for removing large debris or reducing the size of that debris so it's can move through the pump without clogging. Odor control systems, and then electrical equipment. So looking at a pump station, this is a section of one of our designs. The major components to note, obviously you've got your gravity sewer coming in, and this structure here is the wet well. Inside the wet well, in this case, you've got the pump. We call this a submersible style station because the pump typically stays submerged in the wastewater. From the pump, you have your force main. Also inside the wet well, you've got your pump controls. These controls tell the pumps when to turn on, when to turn off, and there's also some controls for alarm elevations. And then you've got your valve vault, where you've got flow control valves such as check valves to keep flow from coming back into the pump station or into the wet well when the pumps are not running, and isolation valves for isolation for maintenance purposes. And in this case, we also have a in-channel grinder upstream of the pump station, again responsible for reducing the size of any solids that may clog the pump. Again, so the previous model was what we would call a submersible pump station. This one, the pumps actually sit on top of the wet well. This is known as a suction lift station. The operation is basically the same. There's a few other things to look at when determining capacity, but essentially the same. Submersible and suction lift stations, typical size we might see between 4 feet in diameter up to maybe 12 feet in diameter. Sometimes if we need much more volume, they'll move away from a precast structure and into a custom design. And depths typically range between maybe 10 feet to maybe 20 feet, sometimes a little bit deeper. So that said, what I've got here is a scaled submersible style station with a 4-foot diameter and 15 feet deep to give you a sense for how large some pump stations can get. And this isn't even an extremely large, but this is what we call a wet well, dry well style station. You can see that there's a substantial size difference. And I'm hopeful that this slide maybe alone demonstrates the, or maybe why some capacity analyses are more expensive or take longer than others, but also for design and construction. These two style stations, they both do the exact same thing. They collect wastewater at a low point. They add energy to the flow via mechanical means, the pump, to move it down the line. But obviously there's a substantial difference in the scale of the two. And just to help kind of clarify the mess on the previous slide, this is a cutaway rendering of a wet well, dry well style station for one of our projects. And this area here is the wet well. So this is where the wastewater is collected. And then on this side of this wall, you've got your dry well. This is where the pumps are housed. And you see you've got suction lines that draw liquid to the pump, and the pump then discharges into the force main and down the line. And then above grade, you've got your admin space. You've got your maintenance space. You've got space for electrical equipment, hoisting equipment up top to pull these pumps to the surface. And then you've also got emergency generator. And then you can't see, the station also had odor control. Some of the benefits of pump stations, because we're using mechanical means, the pump to add energy to the flow means we can move sewage uphill and over long distances. In fact, we can add so much energy to the flow that typically it's the pipe wall itself is the limiting factor on how much energy we can add. Because again, it's pumped flow, the pipelines are smaller than when compared to a gravity system. The alignments are flexible. The force main alignments can be routed horizontally or vertically to dodge obstacles. And because of that, force main depth is typically only 3 to 5 feet. Not always the case, but again, there's generally rarely a reason to go much greater than 5 feet. And then increasing capacity can be relatively easy, and more on that in a minute. Some of the disadvantages of a pump station. Because it is or requires mechanical equipment, there is maintenance from the pump to the valving. Again, rags or other debris can cause blockages. There's reliance on external power. For this picture here, keeping these lights on powering the pump, whoever owns this station is going to receive a monthly power bill. And we'd already talked about sort of the challenges with solids and grit. Ragging can be problematic. And then increasing capacity can be expensive. So compared to my previous slide where I said it can be relatively simple, it depends on many factors. It may be as simple as an impeller change for the pump to increase its output, but with that increased output might come the need for increased horsepower, which might result in the need for emergency generator replacement or bringing in a more substantial service from the utility provider. So it can snowball. So if you're, I'd say if you're lucky, your project, it's as simple as an impeller change, but be aware that sometimes pump station improvements can snowball to be very expensive. And then I also want to mention vacuum sewers. Typically, you'll see vacuum sewers in coastal plains or areas, very, very flat areas. For vacuum sewers, you've got boundary valves, suction pipes, vacuum pumps, and then the collection tanks. So for this entire presentation, this is the only non-Timmons Group image. Everything else is either Timmons Group design or project photo, but I borrowed this from AirVac. They make vacuum sewer systems, and this was just a great, simple overview of what a vacuum system consists of. And we'll start here at the collection tank. This is ultimately where the wastewater will be collected. But from this tank, you see this pipe here down to these vacuum pumps that actually draw air out of this tank to reduce the pressure inside this tank to something less than atmospheric. And that will also reduce the pressure in the vacuum mains to something less than atmospheric. And here we've got a collection sump, and wastewater flows into the collection sump from the building or home by gravity as normal. But when the liquid level inside this sump reaches a certain level, this boundary valve or interface valve will open. And because the pressure inside this main and inside this tank is less than atmospheric, atmospheric pressure will force the liquid up this pipe and all the way to the collection tank. And then once the liquid level inside the collection tank reaches a certain level, the sewage pumps will turn on and move that liquid down the line, either to the next stretch of gravity or another pump station or potentially the treatment plant. So now looking at capacity studies, the heart of this discussion. So the steps that we have to go through to complete a capacity study will be the data collection phase, estimating future flows, obviously the calculations, and then finally communicating our findings to our clients. The primary equation for a capacity study is simply the absolute capacity of a given piece of infrastructure minus its allocated capacity gives its available capacity. Now, the allocated capacity is a combination of existing flows and what we call non-tributary flows for projects that have been recently approved by locality but not yet constructed. So data collection for the infrastructure, the information that we will need to determine its absolute capacity. There's two main types of data. There's assumed data, which would be things like design drawings or as-built record drawings, or GIS. So these are assumed because just because things were drawn a certain way on a plan set does not mean that that's exactly how they were installed. Or things may happen, settling between structures may change the slope of a gravity sewer. And then obviously GIS is approximate. It's a great tool, but it's approximate, rarely trusted for true capacity studies. So assumed data versus observed data. Observed data will be things like a survey or CCTV inspection, where we send a camera on a robot through a collection system to confirm some dimensions or identify obstructions in the flow that might not be available from the surface or from looking at a plan set. And also pump tests. Instead of relying on an engineer's calculations to determine what a given pump rate may be, we will go to the pump station and we will physically test its output. Now determining what existing flows are. Again, assume data. We will use rooftop counts or lot counts, and we will assign a flow factor, a gallons per day per lot, to determine what the existing flow rate in the system may be. Or we can use building size and usage. Is it 1 million square feet of office space or 1 million square feet of warehouse? So those things will determine what kind of flow factor we use. And then acreage zoning is similar to building size and usage, but on a larger scale. We'll look at larger tracts of land, and based on zoning, whether it's agricultural, residential, commercial, we'll apply an appropriate flow factor. And then I mentioned NYT, or not yet tributary flows. I also call these paper flows for projects that have been recently approved but not yet constructed. And then observed flow data. Water consumption records. We can use billing records to determine the amount of flow that comes into either a home or a building or a larger service area. And we'll make the assumption that what goes past the water meter will come out, and that's not always the case, but it gets us closer than assuming a flow factor per lot. There's also gravity flow monitoring, which means we'll take a gravity flow meter and put it into a gravity collection network, and over a period of 2 weeks, 2 months, we will monitor in almost real time what flow rate is moving through that pipe. And then we also have pump run times, and then it's important to note that I always recommend coupling pump run times with a drawdown test. So what that means is, if we have the ability to monitor the number of minutes in a given day that a pump station operates, and we know, because we've measured it through a drawdown test, exactly what pump rate that those pumps are putting out, then we can calculate how many gallons in that period of time, in that day, have passed through that station. So a note on peaking factors. I think this is important. Sanitary collection systems are not designed around average flows. They're designed around peak flows. And so what we have to do is we have to move that peak, or we have to move that average 24-hour flow into a peak flow by using a peaking factor. It's important to note that just about any method of determining a peaking factor is an assumed method. It's an assumed peaking factor. Even if you have observed data through flow monitoring, and you can look at the peak flow compared to the calculated average flow over that monitoring period, that peak is only good for that monitoring period. It may not be representative of a true peak through the collection system at that location. So I think that's important to note. Then on to estimating future flows. Again, we'll use rooftop counts, lot counts, and use a flow factor. Typically, those flow factors will be provided by the locality or the state. Building size and usage, very similar to acreage and zoning, again, using design flow factors. And then we also can use design fixture counts, whether these are water fixture units or drainage fixture units. We can convert those into gallons per minute. What I'll note here is that these fixture counts, the resulting gallons per minute, tends to be extremely conservative because they assume that all fixtures are operating at 100% at the same time. So typically what we will do is we will use fixture counts. We will use the equivalent gallons per minute as our peak flow, and we will actually divide by the peaking factor to back into our average daily flow. And this is just an example of some flow factors for different building usages. And then we also have here an equation. This is from North Carolina. This is an equation for determining the assumed peaking factor for the system. Now onto the calculation phase. So for gravity sewers, Manning's equation is typically the go-to equation. This is Manning's equation, and we can use Manning's equation to calculate the flow rate in gallons per minute with these variables, where M is the pipe wall roughness coefficient. Different pipe materials have different roughnesses. If you look closely, if you were able to zoom into the pipe wall, you might see things like I've got represented here, where PVC is a little bit smoother than a concrete pipe. So we'll use the N factor to account for the difference in roughness between materials. There's also the flow area. And what that means is, if you had a pipe at a given depth, the flow area is literally the cross-sectional flow within that pipe. And we can calculate that if we know the pipe's radius and we know it's the depth of flow. We can use geometry to figure out what that cross-sectional flow area is. And then there's also R, which is the wetted perimeter. And what that means is simply the portion of the pipe wall cross-section that is in contact with water. Again, knowing the radius, knowing the depth of flow, we can calculate the wetted perimeter. And then finally, we have the pipe slope, which I think we all understand is the ratio, the relationship of rise to run of the pipe. And obviously, because it's gravity powered, water will go from high to low. Now, it's important to point out here that Manning's equation has its limitations. Basically, the slope that's input must be greater than 0. If the slope is 0 or negative, Manning's equation breaks down. You will end up with an error. And this is important because, again, it's a limitation of the equation, because not all sewers are perfectly laid. Some gravity sewers are what we call inverted. From flow direction, the inflow of the pipe is actually lower in elevation than the outflow of the pipe. So we can use Manning's equation to determine, or let's say, given a known pipe diameter, a known slope, and either a known or assumed roughness. Typically, 0.013 is a good conservative assumption. And if we know the target flow rate for that pipe, we can then calculate the depth required to move that flow rate. And if the depth required to move that flow rate is less than what the locality will allow, then we say that that pipe has capacity. If the depth of flow required to move that flow rate is greater than the depth allowed by the locality, then that pipe is over capacity and will likely need improvements. And I mentioned some limitations of Manning's equation. I also want to point out that we make some general assumptions. We don't take into account changes in depth from the beginning to the end of the pipe. It's assumed that everything is constant, which is not always the case. We don't account for any inertial forces. So we assume that the velocity profile from the beginning to the end of the pipe is constant, which is not always the case. And again, I've already mentioned the fact that we can't use 0 or negative slopes. So when we get into situations where that is necessary, then typically we'll move to computer simulations. Again, 0 negative slopes, extended period simulations where we can monitor the fluctuations of flow depth over a course of either an hour or a day or several days. And then we can also use it to identify surcharging or potential overflows. So this is an example of a typical output from a gravity sewer model. The green line at the top simply represents existing grade. The vertical lines are your manholes, and the white band through the middle is the gravity sewer pipe. Within that, you see the blue represents the depth of flow, and then the dark blue line represents what we call the hydraulic grade line. And I'm not going to get into too much detail on hydraulic grade line, but the importance here is, in this particular case, you can see where the hydraulic grade line, the HGL, actually exceeds the height of the pipe. And when that occurs in a collection system, that's an indication that the upstream, either manhole or several manholes, may be surcharged. In this case, it's just one manhole, and it doesn't look too significant, but it is a surcharged manhole. That means that wastewater is backing up into that structure. Now, if the hydraulic grade line is affected or rises too far, either due to the size of the sewer not being adequate or potential obstruction, we run the risk of a sanitary overflow. So it's important, again, to note that Manning's equation will not tell you if an overflow will happen, but sewer modeling will. So how do we increase the capacity in a gravity system? Really, there's two main options. There's the increase of slope or an increase of diameter. And I mentioned there was one caveat, and that is, as we talked about, the roughness coefficient. If you were able to make a pipe wall smoother, you could increase its output. But for the sake of this discussion, it's not a practical solution to increasing capacity. So let's focus on increasing slope. Obviously, again, it's the relationship, the ratio of rise to run of the pipe. And if we look at a hypothetical pipe here, a slope of 1%, diameter of 12 inches, an in value, or again, the roughness, pipe wall roughness coefficient, 0.013, and a flow depth of 50%, that pipe at that depth would be capable of conveying approximately 802 gallons per minute. If we change the slope, the output changes from 802 gallons per minute to 1,134 gallons per minute. And it's important to note when talking about changing pipe slope as a means of correcting capacity deficiencies, if your engineer comes to you and says, I've used Manning's equation, and based on Manning's equation, we've identified a single run of pipe that needs to be replaced in order to make the system work, your next question should be, have you created a profile? And the reason, the importance of the profile is because if we change the slope of one pipe to correct capacity deficiencies, chances are that that change will have to be chased downstream in order to make the elevations work. So this one pipe, theoretical pipe that caused capacity problems actually results in the need to replace, potentially 4 pipe segments in 3 or more manholes. Now on to increasing diameter to increase capacity. Increasing the diameter will change the cross-sectional area of the flow and will also change the wetted perimeter. So back to this same theoretical pipe, if we changed the 12-inch pipe to a 15-inch pipe, and we assume that we keep the same 50% flow depth, so the depth of flow now goes to 7.5 inches, you can see the new cross-sectional area of flow. The output goes from 802 gallons a minute to 1,454 gallons per minute. So with gravity sewers, again, there's 2 main options. You can either increase diameter or you can increase the slope. For pump stations, there's several pieces of a pump station that have to be looked at in terms of capacity. There's the working volume, there's the pumping rate, the force main capacity, the electrical system capacity, screening and grinding equipment, the odor control capacity. So working volume, the importance of the working volume is it ensures that a pump does not cycle, which means turn on, turn off, then back on too frequently. When we design, we typically like to limit our pump starts, pump cycle times to no more than 6 starts per hour, so every 10 minutes. And we can calculate the working volume required based on this equation. TP over 4, where TP is the minimum pump cycle time. Again, typically we go no less than 10 minutes. P is the pump rate. And this equation assumes that the minimum cycle time will occur when the influent rate to the station is equal to the pump output, which I've gone through the equations and confirmed myself that is indeed the case. So working volume, minimum working volume is calculated by TP over 4. So a little bit more to help you understand that. Inside the pump station, the 2 primary control levels will be your pump on and pump off level. The pump off level tells the pumps when to stop pumping. So generally, that will set the low water level inside the pump station. Now what happens is as flow comes into the station, the wet well level will rise until it reaches the pump on float. Once the pump on level is reached, the pump will turn on and pump flow down the line through the force main. Until the pump off level is reached, then the pumps will turn off and the cycle will repeat. So looking a little bit closer at these floats, again, we just talked about the pump off level. There's also, sometimes there's a level lower than that where we have a low water alarm. If there's an alarm, what will happen is it will initiate what we call an auto dialer, and that auto dialer via landline or cellular modem will place either an automated phone call or send an alert, a text message to an operator to let them know that there's a problem with the station. Again, as the liquid level in the pump station rises, we reach the pump on float. If it continues to rise, we reach the lag on float, which would turn the second pump in the pump station on. If it continues to rise, we reach a high water level alarm. Again, an operator will be notified. And if it continues to rise still, then we reach this critical elevation here where the level of the wastewater has reached the influent level elevation of the gravity sewer coming in. And that is significant because if the liquid level continues to rise, we run the risk of surcharging the upstream gravity sewer and potentially overflowing into someone's basement, or overflowing from an upstream manhole, or potentially overflowing the wet well itself. And this is all important because an option or potential option for increasing working volume, if allowed by the locality, will be to shift these control elevations up. And by shifting these up, typically we wouldn't want to go any higher than the gravity invert in elevation, but by shifting them up, what it does is it opens up some, or allows for some additional working volume. And it may be the case that for your project, that change in working volume will satisfy the need to keep the pump from cycling too frequently. Now, if that change of float elevation does not do it, then we look at more drastic measures such as replacing the wet well to something larger, or potentially putting in supplemental storage, an additional wet well adjacent to this one, connected by a gravity pipe. And basically, it effectively functions as a larger wet well. I mentioned pump rate. The pump rate for a pump station is determined, or should be set at least to match the peak influent flow rate. So if your project is anticipated to result in a flow rate that exceeds what the existing pumps are capable of pumping, then those pumps will need to be replaced. And there's a bit of a domino effect here, because if the pumps need to be replaced to move more liquid, then there might be a horsepower change, which could result into having to change the emergency generator or increase the incoming line size from the power company. Force main capacity, in general, velocity is or can be used to determine the force main capacity. Typically, we'll design somewhere between 2 feet per second and 8 feet per second. 2 feet per second sets the minimum flow velocity, and that's important to make sure that any solids in the main, there's enough energy to keep those solids suspended and not settle and potentially cause a clog. And then again, up to 8 feet per second is allowed by most localities. Typically, I will design to maybe 6 feet per second. If we get to 8 feet per second, the amount of energy that has to go into the system gets a little high, or tends to get a little high, depending on the length of the force main. So that said, there are other factors to be considered, not just main velocity. Factors such as head loss. What head loss is basically the amount of energy that is lost through a pipeline to move liquid at a certain flow rate. Because that's the energy that is lost, it also means that's the energy that must be put into the system to achieve that flow rate. And so to determine the amount of head loss in a force main, we use Hayes and Williams formula. And this equation basically accounts for L, the length of the pipeline, Q, the flow rate, C, the pipe roughness coefficient, which is similar to the N value for Manning's equation. Different numbers, but the concept is the same. We're correcting for internal roughness of that pipeline. And then D, the pipe diameter. So we can compare, for a given set of variables, we can compare the amount of head loss per flow rate. So if we look at, again, a hypothetical pipe, 12 inches in diameter, 30,000 feet long, and a roughness coefficient, a C of 120, we can plot, for any flow rate, we can plot the amount of head loss that we expect. We call this the system curve. This system curve is neat because it allows us the ability to overlay manufacturer's pump curve, shown here in gray, And where these two curves intersect, where they cross, will determine where that pump will operate. So in this case, that pump will move about 1,000 gallons per minute against roughly maybe 180 feet of head loss. And from other equations, we can determine that that will likely require roughly 115 horsepower motor. And that's important because if we want to increase the flow rate to the station or the flow rate from the station, let's say from 1,000 gallons per minute to 1,250 gallons per minute, we can see that the amount of energy, the amount of head loss that has to be overcome is increased to maybe, I don't know, 245 feet. And in order to achieve that, we're going to need more horsepower. And we're also going to need a new pump in order to cross the system curve at that location. And then finally, we need to look at, is the new point still within the acceptable velocity range for the force main? And in this case, it is. Now, what happens if we change the force main diameter? If we change the diameter from 12 inches to 14 inches, the system curve lays down. I think this makes intuitive sense. A larger pipeline will require less energy to achieve the same flow rate. And what's important to note here is if we look at where the original pump curve crosses the new system curve, it's actually out here by maybe 1,450 gallons per minute. And if you look, even though our flow rate has gone up, the amount of energy that we have to overcome has gone down. But what's important to notice here is just because there's less head loss in the system does not mean that the horsepower requirements are less. In fact, when compared to the original 115 horsepower, we still need more horsepower. We need about 150 horsepower. And again, this is significant because with the horsepower change comes a change in electrical service, whether it's the emergency generator or the line voltage from the local power grid. So certain motor horsepowers require certain voltage. So the available power can be a limiting factor for a pump station. Now, obviously, available power can be paid for or can be increased by paying for bringing in a more substantial service or possibly replacing the emergency generator, but it is going to be a cost. Screening and grinding equipment. Again, screens are sized and grinders are sized for certain hydraulic flow rates. So this is just an example of a grinder, basically head loss per flow rate curve, just to show that they are sized for certain hydraulic flow rates. If the design flow rates are exceeded or acceptable flow rates are exceeded, then a replacement will be necessary. And here's just a photo of what a grinder inside of a channel would look like. We typically see this at a larger pump station or at the beginning, the head of a wastewater treatment plant. And then finally, odor control. So odor control consists of a chemical dosing pump and then a storage tank. And the capacity of the chemical dosing pump is a factor because if flow rate is increased, the rate at the chemical must be dosed is increased. And if the increase in flow puts the chemical dosing pump beyond its capacity, then it will need to be replaced. And if the dosing rate goes up, then we want to make sure that the size of the storage tank is appropriate. So refilling the tank isn't necessary twice a week. We want to see that to be, I've seen as frequently as every 2 weeks. But typically, if we can refill the tank once a month, once every 6 months, that would be ideal. Now, on to communicating our findings, sort of moving away from the more technical side of things. Obviously, verbal, email are both very simple forms of communication. But I think if we determined that substantial improvements were necessary downstream, let's say if it was $1 million worth of improvements, if all I did was provide a verbal notification to my client, hey, guess what, you're going to have to spend $1 million to fix downstream sewer capacity, that probably wouldn't go over too well. So typically, bare minimum is going to be conceptual exhibits. It could be something as simple as what we've got shown here, an aerial exhibit with some PDF markup showing where in the system capacity is a concern or what our plan might be to address that capacity. But depending on the nature of the project and how substantial or even how expensive these improvements may be, it may be necessary to take the conceptual exhibits, to the next level, something a little closer to design level, which might look like this. But again, this gives the client, the owner, and even the locality more comfort that the improvements necessary are adequate, are approvable. Sometimes we have to go into more of a report style we call PERs, or preliminary engineering reports. And these reports are much more in-depth, much more detailed. They provide details that may be necessary, again, for the locality to confirm that the appropriate considerations were given when determining capacity or when designing the necessary improvements to the system. And that said, I'll also include that coordination with the locality is absolutely critical. If your engineer has identified capacity concerns and come up with a plan to correct those concerns, the locality needs to be involved in that discussion. One, to make sure it's an approvable solution, but two, to make sure that additional flows don't need to be accounted for. It may be that the locality has a larger plan for the sewer area and wants to replace a smaller sewer with something larger than what is necessary for just the project flows. And then we'll also provide cost estimates, an OPCC, which is an opinion of probable construction cost, or an OPPC, which is an opinion of probable project cost. An OPPC will typically include things like engineering design, survey, environmental services, permitting, construction administration, things that would give the owner a more accurate view of total project cost. But obviously, the cost is probably the most significant factor, the thing that owners are most interested in. Now, talking about recommended schedule. This isn't schedule for the construction of improvements, but the schedule for the anticipated, the schedule for when in the project life the capacity analysis should be done. Now, I would offer that the last thing an owner may want is to purchase a property, secure funding, maybe go through site plan approval and go through all of these steps just to find out that the downstream sewer is incapable of handling the anticipated project flows, and several hundred thousands of dollars or millions of dollars will be necessary to improve downstream capacity. So my personal recommendation is a capacity assessment should be conducted as early as possible in a project timeline. Sometimes this means, again, before projects or properties are purchased, at the due diligence phase. That way, everyone understands what potential offsite improvements are necessary and what they may cost. So that it's literally the end of that section as early as possible in the project timeline is my recommendation. Now, on to cost variability. Again, not the cost variability of improvements, but the cost variability between capacity analyses, why they differ. And I think the primary thing to point out is no two projects are the same. There's several factors that vary between projects that must be looked at. Things like the locality, where is this project? The existing infrastructure, the relative locations between the project site and the existing infrastructure. And then there are some other factors to consider. So considering the locality, different localities have different records that are available for engineers for determining the capacity of their infrastructure. Sometimes as-built drawings and GIS are available, other times they're not. Sometimes existing flow information is available. Sometimes the locality will require the engineer to go collect updated flow data, real-time, using flow meters. Is a survey required? As far as reporting results, can it be done in an Excel table using Manning's equation, or is a PER required? Or sometimes is a computerized hydraulic model necessary? Existing infrastructure. Is the engineer going to be reviewing, 100 feet of gravity sewer or 100,000 feet? And then pump stations. With the number of factors, that need to be considered inside of a pump station, if there's a pump station that must be analyzed downstream, that's going to add cost and schedule. If we determine that a pump rate is insufficient based on projected project flows, we don't want to assume that we just have to replace the entire station. We're going to take a deep dive into confirming, if we change the pump, do we need to change the generator? Do we need to change the force main? Do we need to bring in a more substantial service from the power grid? Do we need to replace the wet well? So it's going to take a much more involved investigation. Relative locations. Basically, this means where's the existing collection system infrastructure compared to your project site? Is it the case that you've got a large diameter trunk main, going right through your project site? If so, that's relatively simple. Or is the only existing gravity sewer 500 feet away, and it's only an 8-inch gravity sewer, so capacity is more of a concern. So the engineer's going to have to evaluate options. Can we extend a gravity sewer to get to the existing main? Is a pump station necessary? What are the cost differences between the two? And again, the distance matters. Is it 500 feet or is it something much greater? And then there are other factors. Sometimes I'll say engineers simply know some relevant information up front. As an example, I'm working on capacity assessments, 2 different projects in the same sanitary collection basin. And I know that this basin has some real challenges. The existing infrastructure is all very close to capacity. The corridors to make the improvements, capacity improvements, are all very congested. And so the next time that I have to perform a capacity assessment in this same basin, my price and schedule are probably going to increase because I know that I'm going to have to chase improvements further downstream. And then sometimes engineers recognize that certain localities or certain reviewers are pickier than others. And so we will account for that, knowing that we might have to go through several rounds of review and comment before an approvable capacity solution is determined. So with that, hopefully at this point, you've got some understanding of what collection system, sanitary collection system infrastructure looks like, the information that we need as engineers to perform a capacity assessment, and then a better understanding of why there may be so much cost variability between projects. So with that, I will open it up for questions. And again, if I can't get to everybody's question today, please don't hesitate to email me or call me at your convenience. I'll be happy to discuss anything with you. So with that, Sarah, I guess I'll turn it back over to you.
Okay. While we are waiting for questions to roll in here, just a quick reminder to everyone on this webinar today, you will be receiving a certificate of completion post-presentation. So be on the lookout for that via email. Also, we will and are still hosting future webinars. So go ahead and visit our website at www.timmins.com to register for some more upcoming ones. I don't believe we have any questions right now. Chris, it seems like you did a good job in answering all the info right up front.
Maybe, or put everyone to sleep. But for those, again, if there's a question that you want to discuss offline, please, like I said, don't hesitate to call me or email me. I'd be happy to discuss anything with you.
All right. I think that was it. Paul says thank you. Elizabeth says thanks for a very clear presentation. Sounds like you did a good job. So
I appreciate that. And again, thank you everyone for your time this morning. Again, don't hesitate to contact me.
All right. Thanks everyone. Have a great day and be on the lookout for your certificates.